Hello everyone, my name is Ahmed Abdallah. Today I'm going to talk to you about creating a Bittorrent client using Python Asyncio. I'm pretty sure everyone here knows what the Bittorrent protocol is, but just in case, Bittorrent is a peer-to-peer open protocol for sharing files. It's a robust distributed protocol, and I'll explain more about that in the next few slides. And you might be thinking, like, why build a Bittorrent client from scratch? And the right answer to building anything from scratch at your day job is, of course, like, why not? No, I'm just kidding. The real reason I built a Bittorrent client is that I spent a 3-month retreat at the Recurse Center. It's a location here in New York City where programmers can come and pursue any sort of creative or intellectual endeavors they want. And one of the things I wanted to look into was, how does Bittorrent actually work? You should check out the Recurse Center. It's a really cool place. You can get a copy of all these slides later as well. Who uses Bittorrent? Is it still relevant? Is it at all useful? And the answer is absolutely yes. Gaming companies like Blizzard and Eve use Bittorrent for different things. For example, in the case of Blizzard, the desktop downloader is actually a Bittorrent client with a .torrent file hard-coded into it, and helps people get games like Diablo 3, World of Warcraft, as well as game patches, and it reduces the sort of network and bandwidth consumption that they don't have to support using their own infrastructure. Governments and educational institutions use Bittorrent for serving large data sets to users. It's obviously used in the entertainment industry, and you might have personal experience of your own in that regard. Tech companies like Facebook and Twitter have come across readings of them using Bittorrent for doing code rollouts to servers. So there's one article about Facebook getting like significant improvement of rolling out code to their server fleet using the Bittorrent protocol. So I even learned that Amazon S3 supports downloading files through Bittorrent. So any file that you have uploaded to S3, you can put a $torrent at the end of the URL, and you get a .torrent file that you can download. So that's, it's a very relevant thing, especially if you're doing IoT, Internet of Things. So my agenda for today is explain how the Bittorrent protocol works, define some steps for writing a simple Bittorrent client, and talk about why we're going to use Asyncio for this, and then finally go through some code. And first, let's download a torrent file. So the common experience that we're all used to is we'll go to some website, like the Pirate Bay or hopefully something more legitimate. We'll download this .torrent file onto our desktop. We'll open our Bittorrent client up and we'll drag and drop this file in there. And voila, we have our Bittorrent file. And we're going to talk about how this works behind the scenes. And specifically, we're going to write a Python program such that when we say Python, client.py, and we give it that .torrent file, it downloads that torrent file for us onto our computer. So what happens when you turn on your computer and your Bittorrent client program is running? Well, at first you're a single node out in the internet. And when you take that file and you upload it onto your Bittorrent client, your program parses that file and finds this a location of a server known as the tracker. And your client program then says to the tracker, hey, I'm trying to download this file, say Game of Thrones or something, and don't download anything illegal, but your client program will say to the tracker, do you know who else has my file? So it sends an Http GET request, and the tracker will respond to your computer and say, yeah, here's a list of people out there that have the same file that you're trying to get a hold of. And so now that we know who all the peers are in the network, in the swarm that have our file, we'll create a download connection to every single one of these peers, and we'll start downloading pieces of our file. So our plan is to read the .torrent file and get the tracker information out of it. We're going to request a list of peers from the tracker. We're going to connect to each peer and download a piece of this file. And for every piece that we download, we're going to save it onto our hard disk. And why do we want to do this using Asyncio? Well, this problem kind of deals with two things. One is that we want to maintain multiple concurrent connections, one for each peer, and that this is a network I/O bound application. Is that a lot of time is going to be spent waiting for data to come through the wire or waiting to write data. It's not going to be a CPU intensive task. So it makes Asyncio a good candidate for doing this. And what is Asyncio? Asyncio is a way to write single process, single threaded concurrent application where your code yields control from one task to the other at optimal times that you define. And we'll break this down a little bit more. The building blocks for writing Asyncio code are, one, a coroutine. A coroutine in Python is a function that can be paused and resumed. you can yield data from the coroutine and you can send it data. Another task or concept that we need to know of is a task. So now that we have a coroutine, we need to make the coroutine do work. So a task schedules a coroutine. It makes it move one execution step forward. And then finally, we have an event loop, which is something that takes all these tasks and gets them running and gets them moving. So if we had to write a quick fake event loop, it'll look something like this, where we'll have a queue of tasks, and each task object is this thing that's initialized with a coroutine. And we'll just create this while loop that says, so long as we have items in the queue, we'll pop it off, and we know that it's a task object in this queue. We'll say task.execute your coroutine, make it do one step of execution. And we'll say task, is your coroutine done working? And if it isn't, we'll put the coroutine back at the end, or put the task at the queue and go on to the next task. So it's sort of this just cycle of executing task after task after task until the coroutines in that task are exhausted. If you do any sort of front-end programming, Node.js, you're probably familiar with event loop and such programming. And so how do we create a coroutine in Python? Well, as Python 3.5 and above, it's pretty simple. You just put the term async in front of your function definition, and it becomes a coroutine. And within your coroutines, if you want to await or yield control for another coroutine to do some work, you just put this syntax await in front of a coroutine, and that says, hey, give control to this other coroutine to do work. How do we run a coroutine? Well, we import the asyncio package. We get an instance of the event loop, and we say event loop, run until complete, and we give it the coroutine. A few slides ago, I said that tasks execute coroutines, and this is true. What happens behind the scenes here is that the framework will take our coroutine and wrap it for us in a task. That's pretty convenient. And how do we run a bunch of coroutines or tasks together? Well, simultaneously. So one thing to do is you can create a wrapper coroutine, and inside that coroutine you can make use of a asyncio method known as gather, asyncio.gather, and you can give it a bunch of coroutines, and what it'll do is it'll wait until all those coroutines finish before continuing. And so we're going to make use of that. And we're going to schedule a bunch of coroutines to talk to each peer to download our file. When it comes to cooperative multitasking and using an event loop, you normally have one task that's running, and when that task gets to a blocking point, such as waiting for data to come across the wire or some sort of I/O point, the event loop will switch to another task and execute that. So you're just kind of looking at this like quick diagram. You have like a task 1, it's running, it gets to some pause point, another task starts running, and then jumps back to this one. So it's sort of back and forth until all the tasks are exhausted, or your program is done doing the work it needs to do. So when it comes to writing our Bittorrent client, we're going to create a coroutine called download, and we're going to give this coroutine our .torrent file that we downloaded from some shady website, and we're going to read the torrent file and get the information out of it, and we know that it has whereabouts of a server known as a tracker. We're going to connect to this tracker, and we're going to get a list of peers that have our file, and then we're going to say for every peer address that we get, we'll create this peer object and give it, initialize it with the address information. And we'll use this object to keep track of the peer communication in state. And then we're going to say we're going to use the asyncio.gather to start a download coroutine for every single peer. So for peer 1, 2, 3, we're going to say talk to them and start downloading this file. And that pretty much summarizes the program we're going to write. But there's sort of one thing that's missing here, which is that how do these peers save the file to the disk, and who saves this file? And for that, we're going to just create another object known as a file saver, and we're going to give it a queue. And in this case, we're going to create an asyncio queue, where every time a peer downloads a piece of the file, it drops it onto this queue, and the file saver will have a coroutine that says every time there's something in this queue, read it, write it to the disk, and go back to listening to the queue. So we sort of have this producer-consumer architecture. In this case, we also initialize every single peer with this queue so that they know where to put things on when they get a piece downloaded. So our BitTorrent client execution diagram looks something sort of like this. We can't really guarantee exactly what it'll look like. But you'll have a peer that creates a connection, downloads a piece, drops that piece onto the queue, and then goes back to waiting for another piece. And in the meanwhile, the file saver task will say, oh, a piece just came in. I'm going to write it to the hard disk. And then peer 2 might say, okay, I got a piece. I'm going to write it to the queue. I'm going to wait for another one. And then the file saver will say, oh, another piece came in. So it's just this back and forth downloading of pieces and writing them to the disk. And only one task is running at a time. So back to our plan. And the first thing we're going to do is, parse the .torrent file and get the tracker information out of it. So let's open the torrent file. If you go to your terminal and you say cat and you give the file like you downloaded from the internet, you get this sort of text that's somewhat readable, somewhat not. There's no clear structure that we can see out of it, with our eyes. But that's because this file is a byte string file and it's known as BEncoded. And BEncoding is a format that's pretty useful in the BitTorrent protocol. And my slide's kind of cut off here. But with BEncoding, what happens is that it's a way to save bandwidth when you're communicating data in the BitTorrent protocol. And it's terse format to just organize byte strings, integers, lists, and dictionaries. So now that we sort of have this table and we understand how this file is organized, we can take that same .torrent file and decode it by creating an algorithm. And we get this JSON structure that represents the file that we downloaded from the Pirate Bay or wherever. And there's two things to note that are important about this file. One is this announce key. This is the key that specifies the address of the tracker server that knows who in the swarm is up and online and has the file that we want. And the other is this info dictionary. And this tells us about the file we're trying to download. Essentially contains the length of the file, the name of the file, and the piece length. And I'll explain what the piece length is right now. The piece length is essentially, one of the nice things about the BitTorrent protocol is that it takes a file and it breaks it down into several pieces. And that when you come to request a file from a peer, you're downloading these pieces. And each piece itself is broken down into a block. So that's how you're able to piece together a file from many different peers. So we parsed the .torrent file. We got the tracker information out of it. Let's connect to the tracker and get the list of peers. So a tracker is just an HTTP server that responds to GET requests. When we come to form the GET request for getting the list of peers, there's a few statistics, download statistics that you need to send over to the tracker for it to keep track of who's online, who's offline, how much have they gotten. But the most important thing is this parameter known as the info hash. And this helps the tracker know what file we're trying to download so it can give you the right list of peers. And when we come to write the GET request for the peer server, normally some of you might be familiar with using the Python request package by Kenneth Reed, and it's an awesome package. But in this case, we're going to use that AIO package. And one thing I want to stress here is that when you're writing async IO code, you don't want to use the same synchronous packages you're used to. You want to use the async equivalent because the async packages don't block the event loop. So they know that when there's a time when they need to wait for data or IO, they yield control back to the event loop so other tasks can be running. If you have a package that's synchronous and there's no, you can't find an async equivalent, one thing you can do is run that package in a thread or run that function in a thread and have the event loop go and continue without being blocked. So we send the HTTP GET request and we get back this BEncoded data structure. And we know how to make sense of this. And so when we decode it, we get a JSON object out of it, or dictionary. And the most important key here is this peers key. And it's a binary packed IP address in port. And if we decode this key, we get a list of IP addresses and ports of the people that have our file that we're trying to download. So now let's connect to each peer and start downloading pieces of our file. When it comes to working with peers, there are two things we need to deal with. One is the peer state, which is our state between us and the peer, as well as work with a bunch of messages that go back and forth between us and that specific peer. When it comes to peer state, one thing you should know about is the state of being choked. Being choked means that a peer will not respond to requests from you and you should not send requests. Another state to keep track of is the interested state, which means that, hey, I want to download a piece of this file because I don't have this file. So it's a way of communicating intention. So every client starts off in an initial state of choked and not interested. And we want to get to a cooperative state where we are unchoked and we're interested. And for that to happen, we have to wait for an unchoked message, and we have to send an interested message. So let's look at, when it comes to the peer state, we'll just create this Python class to keep track of two Boolean fields. One is peer choking, is the peer choking us, that as in they don't want us to download data. And is, are we interested? Do we not have the complete file, or does the peer not have the pieces of the file that we want? And therefore, we have no use for this peer. And we also have a download coroutine that we'll fill out in a little bit. So when it comes to the peer exchange between a client and a peer, the first thing we'll do is we'll create a TCP connection to that peer. And then we'll say, hey peer, we send it a handshake saying, hey, we're trying to get a hold of this file. Can you help us out? And peer will sort of confirm like, okay, I'm ready to work with you. And we just sit and wait now for the peer to give us an unchoked message. And when we gives us this unchoked message, we say, okay, we can send a request for information. And the first thing we're going to do is we're going to send it, hey, we're interested. Can you help us with getting a piece of this file? And the peer will respond back to you and say, with these one of two types of messages, which is a have message or a bit field message. A have message is a single message that says, for piece 7, I have it. For piece 8, I have it. So you're just going to have a stream of these have messages denoting each piece and whether or not the peer has it. When it comes to bit field, it's an array where the index of the array has a Boolean that represents whether or not the peer has that piece. So it's just essentially for all the pieces, I either have them or I don't have them. And this is important because that peer may not have finished downloading that file itself. So it's like it just started downloading. So it's only sharing with you what it knows. So you need to keep track of this information. And then what we're going to do is we're going to send a request message to that peer and say, hey, can you give us block 5 of piece 7? And it'll respond back to us with a piece message saying, here you go. And we're going to write that to the disk. And so we just keep doing this back and forth until we have our entire file. When it comes to constructing the peer handshake, it's a pretty standard message. The first thing you do is you give it like the protocol length, the protocol name, reserved bytes, the info hash, which is the hash of the dictionary of the file we're trying to download, and then a peer ID so that it can identify who's unique. But really the most important thing when sort of like looking at this snippet of code on the left, and I don't know if you can see it well, is that before we open a connection, I have this await call. Before I write, I have this await call, and before I read from the buffer, I have an await. One thing that's nice about Asyncio is that you can see where your program will yield execution from one task to another. So every time there's like a I/O blocking operation, I can kind of see, oh, right here, my code will jump to another task. Whereas if we were using threading, we don't really know when our thread will get swapped in or swapped out for another thread, and that if we want to enter a critical section, we have to explicitly acquire a lock, do some work, and then release the lock. So Asyncio code is just like a little bit easier to read and say, here, this will switch off, something else will happen. So it can help you reduce race conditions. It doesn't guarantee you won't have race conditions. The rest of the messages between a peer and a client are pretty standard. They all have the format of message length, ID, and then the payload of that message. And this is a table that represents all the messages, the remainder of the messages. So for example, when we look at the keep live message, the first part is always the length, which is 4 bytes that denote how long it is. And the keep live message is 0. There's nothing. It's just like a ping. When it comes to like the choke message, the first 4 bytes have denote a length of 1. And then what you need to do is read the next set of bytes, which in this case is just 1. And that 1 denotes the ID. And when we read this ID parameter and we look it up, we can say, oh, we got a choke message. And so the second parameter, aside from the keep live, is always the ID. And you use this ID to know what message it is you're getting. And you use the length to know how much of the buffer you need to read to capture that message so that you don't run into reading parts of other messages. And the off by 1 errors here will kill you. And one thing to note is that the bit field and piece messages can vary depending on how big the file we're trying to download and how it's broken up. So we'll just create this while loop inside our download coroutine, and it will say, keep reading from the buffer, get the first set of items in the buffer to find out how long the message length is, and then get the message ID from which is like the 5th byte. And then we just write this long if statement of if you get a message ID for this message, do this. If you get a message for that message, do that. And so you just handle all the different messages that you can possibly get. And the one thing to know that's kind of important is here, like when you get an unchoked, you want to say, okay, we're interested. And if you get a piece message of the file we're trying to download, we want to write that to the queue so that our download task can save it to the disk. And then finally, if everything looks good, maybe we'll want to request a piece. And one thing to know that's important about requesting pieces that I won't be going into is that there are different strategies for how you request a piece. One strategy is downloading the rarest pieces first. Because if your peer is somebody that's, they just popped into Starbucks, got a latte, opened their laptop, and then as soon as they finish their latte and close their laptop, and they might have been the only person that had that piece of the file, you're kind of going to get screwed. So you don't always want to download in the same orders. And then finally, now that we connected to each peer, we started communicating with them, and we started getting pieces of the file that we want. We're going to just write each piece to the disk. And this is a pretty simple, pretty trivial thing to do, is that in our file saver object, we'll create a coroutine called start, and it's just going to run forever, and it's going to just be reading for items from this queue. And every time somebody drops something into this queue, we'll save it. And if it gets an empty item, like a none object, we'll take that as a signal to mean that, hey, there's no more, don't expect any more data to come to this queue, just exit. And that ends that task. So to bring it all together, we created a download coroutine where we read the .torrent file, decoded it, we reached out to the tracker, we got a list of peers, we created a queue for saving file pieces, and we created a file saver task that'll write the pieces to the disk, and we created a peer to keep track of the peers that we communicate with and the states and the messages we get back and forth. And that's pretty much our Bittorrent client for downloading a file. One thing I'm not going into here is uploading. So right now we're only leeching. That's something you could easily implement if you look into it. If you want to see this code in the entirety of the thing on GitHub, just go to simply amazing pygotham BitTorrent. And this is a pretty simple BitTorrent project. There's a lot of things you can do to make it more full-fledged like the other torrents that you download or BitTorrent clients that you get. One BitTorrent client that I came across that I thought was really interesting is called WebTorrent. And this client will play a torrent movie for you as it is downloading it, instead of waiting for the entire file to come. So you can probably guess that the piece download strategy is in the order of the file, so that you can watch it without getting everything. There's just plenty of things to look into. If you want to learn more about Asyncio, I actually enjoyed the chapter in the book 500 Lines or Less, a web crawler with Asyncio coroutines. It just kind of walks you through creating Asyncio from the ground up. It just gives you a little more in-depth insight into it. And one project, open source project that I really like that uses Asyncio is Python Home Assistant. It's a home automation platform. And one really nice thing about Home Assistant is that it's got 8,000 stars, which is for a Python project, if you convert to JavaScript stars, it's 90,000. It's so that's pretty winning. Thank you for your time. Feel free to reach out to me for questions afterwards or anything. That's the end of my talk. You have time? Yeah. Go ahead.
I was just wondering how you deal with error handling. When you feel wait,
Yeah.
and then it blows up or your internet connection goes out, does it just hang or does it return to the asynchronous function or what happens?
So if there's an error, it'll interrupt your program. And so when I come to create a connection, I'll wrap it in another Asyncio call called wait4, and I give it a time limit. And I say, do this thing. And if you don't do it in 10 minutes, capture the exception and maybe try again. So that's one thing I'm not showing any error handling code in the slides. You'll just take up space. But essentially, yeah, a connection can fail and you have to anticipate it failing.
But you can keep it nice and clean and readable even with the error handling.
Yeah, you can capture it.
Is there a checksum for every piece so a peer wouldn't send you a malicious content?
Yes. So one thing I didn't go into is that the .torrent file has a key called pieces. And so for every piece, when you download it from a peer, you take the hash of it and you take the .torrent file, which has that same, hopefully has that same hash, and you compare them. Because a peer might send you some arbitrary code or file or whatever, and it might not be the thing that your .torrent file is describing. It still doesn't mean that your .torrent file is going to get you the movie or file you're trying to download. It just means that it's going to get you the file it says is going to get you.
When you were developing the system, did you consider other asynchronous frameworks? And specifically, could you compare your experiences developing async versus
Yeah.
Celery?
So I didn't try with Celery, and the guys tell me to stop, but I'll answer this question real quickly. I wrote a version of this on top of the select, just doing my own custom event loop. Then I applied for this talk, and I was like, I'm going to do this async IO, and the talk got accepted, so I'm like, I'm going to figure out how to do this async IO. I considered doing it with threads, but I just didn't think there would be anything that would surprise me. But yeah.